We've looked at functions and we've defined what a function is. We've looked at how to deal with equations and functions. We are going to now look at graphs and how we can represent functions using graphs and what kind of graphs are functions, because not everything is a function. So the big question today is, how can I represent a function as a graph? And I would throw on there as well, what kind of graphs are these magical things called functions? So first, let's make sure we all have the necessary vocabulary that we need. We talk about a coordinate plane. It's a plane, it's a sheet of paper, if you will. It's a flat space containing a horizontal x-axis and a vertical y-axis. And within this coordinate plane, we have these things called ordered pairs, x, comma, y. These numbers give the location of a point on the graph. The first number is the x-coordinate, the second number is the y-coordinate, and you know what? It's sometimes difficult to remember which is which, but they're called an ordered pair. And one reason they're called an ordered pair is because it's alphabetical order. X comes before y in the alphabet. And this is what the coordinate plane typically looks like. The horizontal axis is our x-axis, and the vertical axis is our y-axis. And as we go up on this, we look at positive numbers, and as we go down, we're talking about negative numbers. As we go to the right on this x-axis, to the right are positive numbers, and to the left are negative numbers. And we can scale our axes to whatever's appropriate. The default is going to be 1, 2, 3, and then up 1, 2. Each one of these lines, each one of these grid marks is going to be one number, one unit. 1, 2, 3, 4. 1, 2, 3, 4. Then this would be -1, -2, -3. Same this direction, -1, -2, -3. I'm going to put a point down here. Let's see if we can't give the ordered pair that goes with this. There's a point. I would like you right now to write down what the coordinates of that point are. So my hope is that you wrote down -4, 2. Because we go back 4 units, the x component, the x location is -4, and we go up 2 to get to that point, so the y coordinate is 2. So here's our first example. We're going to graph the equation y equals 12x with domain 0, 2, 4, 6, and 8. And the way we're going to graph this function is we're going to make an input-output table. So it's y equals 12x and our domain 0, 2, 4, 6, 8. So those are our inputs. Those are the values of x that we want. Now we need to find the values of y. And this rule says that we're going to do 12 times x. Well, 12 times 0 is 0. 12 times 2 is 24. 12 times 4 is 48. 12 times 6 is 72. And 12 times 8 is 96. So now what we need to do is we need to plot a point for each one of these ordered pairs. I want to graph this function. So 0, 0 is right here. Now, with this problem, it does not make sense to have the y-axis go by 1 unit each time. It would not be a good choice to make this 1, 2, 3, and so on, because we have to get all the way up to 96 as a y value. So we need to rethink what we're doing here. So here's 0. There's our origin. I'm going to set my x-axis to go 2, 4, 6, 8. My x's go by 2, it makes sense to set my x scale to go by 2 also. So this first mark is 2, then 4, then 6, then 8. What does it make sense to have the y-axis go by? We need to get up to 96. Well, I'm actually going to go by 24. So this first line represents 24, then 48, then 72, and then 96. And I'm going to represent each one of these ordered pairs in the table as a point on this graph. So 0, 0, that's going to be right there. 2, 24 would be there. And then 4, 48, 6, 72, and 8, 96. Written as an ordered pair, this would be 8, 96, like that. And now do not connect the dots. This is a function that only has inputs of 0, 2, 4, 6, and 8. It does not have inputs in between 0 and 2, so there should be nothing in between these two dots. This is what our graph looks like. This graph represents the function y equals 12x for the domain that was specified. In the second example, we have a table showing the points per game for Kevin Garnett for the first 10 games of 2014-15 season. We can examine this table and see that this is indeed a function because for every one of these input values, there is only one output. In the first game, he scored 34 points. He can't score 34 points and 7 points in the same game. He's going to score some number of points in each one of these games. This is indeed a function. What we want to do is we want to graph this function. And to do that, we need to start by choosing a scale. We need to decide how much each unit on each axis is going to represent. And then we plot the points. So let's talk about how to do that. On the x-axis, we're going 1, 2, 3, 4, 5, 6, 7, 8. Count the number of spaces that we have across the bottom. Do we have enough for that? And yeah, it turns out we do. So on the x-axis, I'm going to make each one of these 1. 1, 2, 3, 4, 5, 6, 7, 8. They fit just fine. I don't have to worry about using any other number for this scale. On the y-axis, however, find the biggest number in this table. The biggest number in this table is 34. For 34, I don't have enough space to just go by ones up the y-axis. So we need to pick a different value. And to decide what that value is, let's count how many units there actually are on the y-axis. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 spaces going up that side. So to get to 34, if I go by 2's, if I make each line worth 2, that would get me up to 28 if there are 14 spaces. So that's not big enough. Would 14 going by 3's, would that work? Would it work to go 3, 6, 9, 12, and so on? Yeah, it would. That will actually get us up to 42. So let's go ahead and label our axis, and we're going to go by 3's. And this is not the only way that you could do this. It doesn't really matter, just as long as your scale is consistent, meaning it stays the same. So 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, and 36. And we don't have any values higher than 36, so we can stop there. And now we need to plot the points. 1, 34. 1, 34. We go up from 1 up to 34, which would be approximately there. So pause the video and attempt to plot all of these points, and then start the video again and see if you put them in the right spots. So check your points against mine. Your graph should look something like this, and this is what's called a scatter plot. These points are scattered across the coordinate plane, and we are not connecting the dots. In this example, we have a graph. We want to write a function rule for this graph. We want to write an equation. So first thing we do is we're going to make a table for this graph. So we have to read the ordered pairs. And you'll notice that this graph isn't labeled with a scale, and when the graph is not labeled with a scale, we assume that each mark on the x and y axis represent 1 unit. So the first ordered pair is at 1, 2. So in the x row we put 1, in the y row we put 2. And then the next one is 2, 4. And the next one is 3, 6. And what we want to do is we want to find the relationship between the inputs and the outputs, and what can be helpful is to sometimes use words before we write the function rule. So how do we get from 1 to 2? Well, we could add 1. 1 plus 1 is 2. But is 2 plus 1? No, 2 plus 1 is not 4. That's ridiculous. So what else can we do to 1 to get 2? Well, we could multiply 1 by 2. 2 times 1 is 2. Is 2 times 2 4? Yeah. Is 2 times 3 6? Yes, it is. So multiply inputs by 2. This is my verbal model. Now we take that verbal model and we write down a function rule. We could write y equals 2 times x, or we could use that function notation, that f parenthesis x instead of y equals 2x. And remember, this f parenthesis x, that's just a fancy name for y. And the last thing we're going to look at are graphs and how we know whether or not a graph is a function. So here are two graphs. There's a red graph, there's a blue graph. One of these graphs is a function. The other graph is not representative of a function. And I would like you to take a moment and think about the definition of a function and decide which of these is a function and which one is not. So pause for a moment, then press play. Okay, so let's look at the red one. Let's look at any value of x. Let's say x equals 1. If we go up or down from x equals 1, there's the ordered pair for x equals 1. For x equals 2, there's the ordered pair. For x equals 3, there's an ordered pair. X equals 4. X equals 5 would be way up here. X equals 0 would be here. Negative 1, x equals negative 2, and x equals negative 3 would be way down there. And for each value of x, there is only one ordered pair. Above each one of these x values, there's only one point on the graph, or below. If we look at the blue graph, for this value of x here, there's y. For this value of x, there's y. For this value of x, there's y. But as we get in here, what about x equals negative 1? Well, for when I say, what is the y value for x equals negative 1, you're going to go, well, which one? Because if we look up and down from negative 1, there's 1, 2, 3 different points that would be negative 1 comma something. So that particular input has more than one output, which makes this blue graph not a function. For the red graph, every input, every x value, has exactly one y value that is paired up with it, and that leads us to something, the vertical line test. We use the vertical line test to tell if a graph is a function. And if we can draw a vertical line on the graph, and that vertical line passes through more than one point anywhere, that graph does not represent a function. So a quick sketch. Here's that first one that we had. If I draw vertical lines, is there any place where a vertical line touches the graph more than once? No. But if we look at that blue one, and we draw some vertical lines in here, there's several places where these vertical lines cross more than once. So this one is not a function, while the red one is a function. So there we go. We have reached the end of our time together. Go forth and look at some fun functions as graphs.